Welcome back to Honors Calculus. In this video, we're going to be looking at the definition of a limit. All right. Well, mathematically, the definition of a limit is more straightforward than it seems at first glance. But before we even get there, what do we mean by a limit and why do we care? The idea of a limit is a step towards a theoretical footing for the idea of continuity for a function. In a previous algebra course, you probably were taught that a function is continuous if you can draw its graph without lifting your pencil, which is useful, but not really practical in the sense of, okay, if I can do this, I have continuity, but how do I know when I can't do this? And so we are looking for a theoretical foundation to define continuity, and the limit is the tool that we use to do that. All right, so I'm going to start by writing out the terrifying definition. All right, this definition is important enough that I'm even going to label it as definition. All right, we start with a function. I'll name that function f. It's a real valued function of one real variable. The limit of f at a point C in the real numbers has a value L in the real numbers if and, oops, getting ahead of myself. And since that's such a mouthful, we generally write it symbolically. When we're talking about limit, much like sine and tangent, the limit operation is just written using the first couple of letters, LIM, at a point C in the real numbers. I'm going to express that by putting X right arrow C below the letters LIM. And we read that as X approaches C. So the limit as X approaches C of the function that we care about, which in this case is just f of X, is equal to L. And then symbol soup. For all epsilon greater than 0, there exists delta greater than 0. All right, so two Greek letters right off the bat, epsilon and delta. Epsilon and delta are going to be used here to represent very small numbers. Like values of epsilon, when we use this in a practical sense, are things like 0.01 or 0.000001 or 10 raised to the negative 100 power. Those are all practical values of epsilon that are actually used in various different applications. All right, finding a specific value of epsilon is useful, but the definition says that for every value of epsilon, there is some delta greater than 0. Again, we're assuming delta means a relatively small value. ST, the abbreviation for such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus c is less than delta. And the entire point of this video is to make sense of this definition. That's all we're doing right now. And for most students, the best way to make sense of this definition is to analyze it graphically. So consider some coordinates here. We've got our x-axis, we've got our y-axis, and we've got the graph of y equals f of x. And I've got a point right here that I'm going to call my point C. I can see, right, there's my value, and the value of the function here is what I'm going to call L. We'll see why the value of the function is the tool that we want there when we actually get around to talking about continuity. But when the function is defined and is continuous, that's going to be one of the criteria, that the limit is the value of the function. But what this is actually telling us is that I want to pick some range around L. So the distance above and below L that I'm looking at here is a distance of epsilon. And I'm going to draw in some horizontal lines. And the claim of this definition is that no matter how wide or narrow I draw those horizontal lines, that there must be a way to draw some vertical lines centered around C, a distance to left or right of C measured as delta, so that it draws a box around the function and the graph exits the box on the left and on the right, not on the top and bottom. Right? We can draw a box. No matter how wide or narrow I name this thing, we can always draw a box so that the graph exits the box on the left and on the right, and not on the top or on the bottom. One thing that's going to be useful to us is that there's not a unique value of delta. Here I've drawn a value of delta that worked. I could have drawn that box instead. Once you find a value of delta that works, anything smaller than that also works. And that's going to be very useful to us. So if we're thinking about this graphically, I guess one of the important useful tools is to think about when this is not going to work. And I've hinted at this is a tool towards continuity. We're looking for a formal definition of continuous functions. So let's think about functions that are not continuous. Y equals 1 over x is generally the poster child of a discontinuous function. We know what the graph of this thing looks like. I could use computer software and draw it nicely if I cared, but I don't really care about that much detail right now. At x equals 0, the y-axis, it does not matter how narrow or wide I draw my box here. It is impossible to find a window where the graph does not exit through the top and through the bottom. It is impossible to do that, no matter how big or small, or how tall or short I draw this graph. It's never possible to go left and right far enough, because it just keeps going up and keeps going down forever. You can never get there. And so that's a nice way of thinking about when a limit is not going to exist. Piecewise defined functions are another place that we can run into some trouble with continuity. Here I have a relatively simple one. Y is equal to 1 if x is less than 0, and y is equal to negative 1 if x is greater than 0. So that's a graph that looks something like that. And at x equals 0, no matter how wide I draw this, I'm going to run into trouble. Maybe I can draw the graph so that we're way up here. I can draw my epsilon window so I'm way up here. But that's way down there. That is way below the box that I drew. And so, once again, it's impossible to draw the box so that the graph goes out through the left and through the right. I mean, it goes out through the left, but on the right, it's just way below it from the beginning. All right, so those are things that are going to cause us to have problems. And thinking about those pictures, I think, makes it a little bit more sensible what we're trying to do here. We say that this limit DNE, or does not exist, in both of these cases. All right, so when it is impossible to find the value of delta that we talked about in the definition, we say that that means that the limit does not exist. So as an example, I claim that the limit as x approaches 3 of 2x minus 5 equals 1. How did I get that value? Well, plug in 3 for x. 2 times 3 is 6. 6 minus 5 is 1. 2x minus 5 is a linear function. And I know that linear functions are always continuous. We're going to try to prove that a little bit later, but I know that from previous courses. And so because I know that this should work, which is why I make the claim. I don't just say this is true. I claim that this is true. We need to justify that in some way or another. So I want to find a value of delta that will satisfy the definition of a limit when epsilon is equal to 0.01. In order to do that, I need to remember what is the definition of a limit. Well, we want that the absolute value of the function, which in this case is 2x minus 5, minus the limit value, which in this case is 1, I'll put some serifs on my 1 so it doesn't look like an absolute value bar. We want that to be less than our value of epsilon. And our value of epsilon here is 0.01. Right? So if we want that to be the case, we can do a little bit of cleanup. 2x minus 5 minus 1 is 2x minus 6. That's the same thing as 2 times the quantity x minus 3. And remember, you can take a constant outside of the absolute value. The absolute value of 2 times x minus 3 is 2 times the absolute value of x minus 3. And then dividing by 2, we get that the absolute value of x minus 3 must be less than 0.005. All right. So we have here absolute value of f of x minus L less than epsilon. And our goal was to get the absolute value of x minus c is less than delta. In this particular problem, c was 3. So our goal was to get the absolute value of x minus 3 is less than delta. So delta equals 0.005 will work. Any value of delta smaller than that will also work, but delta equals 0.005 definitely is a value that works, and that's good enough for me. All right, so that's evidence that this is going to work. But evidence is great, but not the end of the story. I want to prove that this is going to work. And so the definition of a limit says that for every value of epsilon bigger than 0, we have to be able to find a delta. That's where we start. Let's let epsilon be some number bigger than 0. I don't know what number. It is just a number that's bigger than 0. That's all I know. And somehow that's going to be enough. Now, whenever you write an epsilon delta proof, it always starts with scratch work. The scratch work is not part of the proof, and so it should be written separately from the proof. And in a traditional calculus course, or even in academic writing, whenever a mathematician writes an epsilon delta proof, they write all their scratch work, and then they crumple it up and throw it away, and they don't show it to anyone. And by crumpling it up and throwing it away and not showing it to anyone, the proof ends up looking like black magic. And so that's something I really want to stress here, is that I'm doing scratch work. It's not what I'm actually writing, it's off on the side. And by hiding it, this proof would be black magic. To show you what I mean, we always start here with our end goal, the same way we did before. Right? Our goal is that we want the absolute value of our function, which in this case is 2x minus 5, minus our limit value, which in this case is 1, to be less than epsilon. And by rearranging that, exactly the same way we did before, just with an unknown epsilon instead of with a particular value, we get that the absolute value of x minus 3 should be less than epsilon over 2. And again, as we saw when we were looking at the specific numbers, absolute value of x minus 3 less than delta is what we're looking for. All right, so that's our scratch work. And that's why let epsilon be greater than 0 and let delta equal epsilon over 2. Right? If I was presenting this in a professional context, that's all I would write. I would not write any of that scratch work out. It would just be hidden off to the side where, someone might stumble across it later, but probably not. And the whole point of delta is to assume that the absolute value of x minus c, 3 in this case, is less than delta. So we have the absolute value of x minus 3 is less than epsilon over 2. Again, that's what we came to in our scratch work. But we're not including the scratch work. The scratch work is hidden. It's not actually part of the proof. We're pretending we never wrote it down. It just has all the answers we need. So assume that the absolute value of x minus 3 is less than epsilon over 2, and consider the absolute value of f of x minus L, which is equal to the absolute value of 2x minus 5 minus 1, which is equal to the absolute value of 2x minus 6, which is the same thing as 2 times the absolute value of x minus 3. Again, it's the same thing we did in our scratch work, but we're pretending the scratch work doesn't exist, so we're writing it out again. But then we use the assumption we just made. We have that absolute value of f of x minus L is equal to 2 times the absolute value of x minus 3. And since x minus 3 is less than epsilon over 2, 2 times x minus 3 must be less than 2 times epsilon over 2. And 2 times epsilon over 2 is equal to epsilon. So we get that f of x minus L is less than epsilon, right? Playing a bit of snake here. There's the part that actually matters. And that finishes our proof. Okay, black magic, right? Let's go through the whole process again. I started with scratch work. I knew what I wanted to conclude, and I did some work to figure out where I would have to start in order to conclude that. And then I throw my scratch work away, and I write down my proof. Let epsilon be bigger than 0, let delta equal the thing that I found in my scratch work, and assume that absolute value of x minus c is less than delta, because the definition of a limit says that we care about what happens whenever this is the case, absolute value of x minus c less than delta. And we care about what happens to the absolute value of f of x minus L. So that's the next thing we do. We write down the absolute value of f of x minus L, we plug in what we know, we go through and do some algebra. It should be very similar to the algebra we did in our scratch work, because our end goal is to end up with the thing we ended up in our scratch work, so we can replace it with the function of epsilon we wrote at the beginning. And as soon as we do that, we will conclude that the thing we have is less than epsilon. That's what we were going for. We got it. That gives us our proof. onto a more complicated one. Here, we want to prove that the limit as x approaches 2 of x squared plus 4x plus 7 is equal to 19. And again, where did we get that 19? Well, if you plug in x equals 2, you would get 2 squared, which is 4, 4 times 2, which is 8, and 4 plus 8 plus 7 is 12 plus 7 is 19. So it should work. It seems like it makes sense. We just need to go through and check out the details. All right. So we start off our proof the same way we did before. Let epsilon be greater than 0 and define delta equals, well, I don't know what yet, but I'll leave a space. And then we assume that the absolute value of x minus our c, which is 2 in this case, is less than something. What's that something going to be? Well, let's go off to the side. We know that our end goal is to get the absolute value of f of x, which is x squared plus 4x plus 7, minus L, which is 19, to be less than epsilon. And we can clean up a little bit. X squared plus 4x plus 7 minus 19 is just x squared plus 4x minus 12. And that factors, that's x plus 6 times x minus 2. And again, the absolute value of a product is the product of the absolute values. And we get that the absolute value of x minus 2 is less than epsilon over x plus 6. All right. So we've got an inequality and we've got x's on both sides. So if we plug that in, it doesn't actually help us any. We need delta to be a constant. So we need to do something further. And something further very often takes the form of, let's assume that delta is less than 1. Because if delta is less than 1, then we can do something with what we already know. And if we found out that the value of delta for our particular epsilon was bigger than 1, we could just use a smaller value anyway, right? If delta equals 5 works, whenever absolute value of x minus 2 is less than 1, it is also the case that the absolute value of x minus 2 is less than 5. So if we ended up that we could have used a bigger value, the smaller value will still be effective and efficient. So if we assume that delta is somewhere less than 1, that means that the absolute value of x minus 2 must be less than 1, which means that negative 1 is less than x minus 2 is less than 1. I care about what's happening to x plus 6. Right? To get from x minus 2 to x plus 6, I'm going to need to add 8 to all 3 sides of this inequality. And I get that 7 is less than x plus 6 is less than 9. All right. And that's getting us somewhere, but our x plus 6 is in the denominator. So remember, if we take reciprocals, that changes the direction of the inequality, right? If a is less than b, then 1 over a is greater than 1 over b. So I get that 1/7 is greater than 1 over x plus 6 is greater than 1/9, or in the other direction, 1/9 is less than 1 over x plus 6 is less than 1/7. Right? The fact that it's not so small as 1/9 is not a big deal. The only thing that I really care about is that it's going to always be less than 1/7. So after the scratch work on my scratch work, I can go back to what I had just off the top of the screen here. Absolute value of x minus 2 is less than epsilon over x plus 6. And since x plus 6 is less than 1/7, this is less than epsilon over 7. And that was a lot of scratch work. But again, that was all just scratch work. But it gave us a value of delta. So I take that value of delta, I come way back over here. I set delta equal epsilon over 7. Although that doesn't quite work because I did make another assumption. All right, well, we can fix that. We'll set delta to be the minimum of epsilon over 7 or 1, whichever is smaller. I'm fairly confident that epsilon is going to be a small number. As we saw in our first example, epsilon equals 0.01 is a very common thing. But just to be on the safe side, we'll take the minimum of the two values and see where we can go from there. All right, so we set that value and we consider the absolute value of our f of x, which is x squared plus 4x plus 7, minus our L, which is 19, and we do our algebra. And we do our algebra. And everything looks the same. And then we make the claim that we came up with over here. X plus 6 has to be something smaller than 7. And x minus 2 has to be something smaller than epsilon over 7. And all told, that's equal to epsilon. Our proof is a lot shorter than our scratch work. And again, that's a fairly common thing. That's just how these things go. All right. And so I'll end with one for you to try. Um, Prove that the limit as x approaches 5 of 4 minus 3x is equal to negative 11. Again, how did I get that negative 11? I took 4 minus 3x, I substituted in x equals 5. 3 times 5 is 15. 4 minus 15 is negative 11. It seems like it should work. Your task is to prove that it actually did. See where you can get to on that, and I'll see you in the next video.